Oh, Bryce. Oh, Bryce.
Bryce, why would you say that? That's not.
I don't know if you guys noticed, the one thing that probably bothers me about anything when you start calling me easy.
But you know that's not true. I was a teacher in the school.
Yeah, exactly. Alright, so you guys got 70 seconds?
Yeah. Yeah.
Cool.
7.0 times 10 to the.
I think that Senor Bud is harder than Mr. Grammar.
It's fun. No, that's a joke. Say.
Why you just have dresses?
No, it's not that I'm hard, it's just I teach harder material.
I think this is.
And you're pretty hard.
Well, you don't throw around extra credits.
But I let you guys get 10%
Administration.
Yeah. Did what's her name have a choice when she said no to giving that marriage thing to the gay couple? No, what's her name? The one that refused to give the marriage certificate to the couple that.
No, yeah, you said you said quitting. Or said that girl.
Sorry. Okay, here we go. We're going to continue talking about current and resistance today. What did we say current was yesterday?
It's the rate at which an electron charge pass through a given area.
Okay, it's how fast electrons move through a certain area.
Yeah.
Okay, that's what current is. What's wrong?
Cole's just mad because he had dirt on his face all last time.
Stop.
Oh.
You got food on?
Yeah, that's all.
Well, he didn't do it.
So, when you turn on a light switch, the light comes on almost immediately, correct?
Correct.
Okay? I wonder why that is.
Electrons go fast.
Ooh, do they?
I thought,
They go
Electron?
is it actually that when like a current goes through the wire, it's not actually the electron going from point A to point B, it's like a rod being pushed.
A rod?
Like, a bunch of videos like explain it like electrons are right next to each other and it just pushes this one end closer to the other end.
The group of electrons?
Yeah.
Yes.
Okay.
Yep. We want to talk about that a little bit today. Okay? So, everyone turn in your books.
Nice. Give me the Roy.
He's dancing. Give me so much
Yeah,
tightness. Oh my gosh. I just put the phone in here.
Yeah, laying in the grass wall.
Yeah,
That's so funny. She's like, it's a kid lecture. I was like,
About
it doesn't look like tennis. She's like, we're right there. I was like, oh. What
I said that to my wife, and she's like, you need to encourage his masculinity, that he doesn't have to be tough to be a man. You don't want a homo son. I was like, oh, okay.
What?
Well, like,
That's not true at all.
So.
That is not true.
did you just self-identify yourself? You came out.
He's coming out of the closet.
All right.
That's such a random
Name 1%, name 1%.
Okay, so,
What page?
sorry. Well, I don't
What'd you
know,
say?
because it's different for me. It is section 3.
Actually,
The next page after section 3, the start of section 3.
We're all homos.
I don't know your page number. I only know my page number.
bro, that's like 580 something, 590. But Steven, we're all homos. Homo sapiens.
It is 567.
You mean 97.
Kramer.
Looks like a 6 upside down.
That is what it
Okay.
That's a true.
My page number is 611. Alright, so we're going to talk about drift velocity. Okay, so when you have a potential difference that is applied across a conductor, so let's just say we're talking about the wire that connects a switch to its leg. Does that make sense? An electrical wire. Not an electrical tube, an electrical wire. Okay. Alright. Okay, so the force due to the field sets the electrons in motion when you flip on a switch. Okay? When you flip off a switch, I don't know if you guys understand probably how a light switch works, but it's basically like if this is a wire, Okay, the switch, when it's off, it disconnects the wire, the wire coming in versus the wire going out. So when you flip a switch off, it disconnects the two wires so the electrons cannot flow through. Does that make sense? When you flip a switch on, it connects them and allows the voltage from, you know, your electric box that comes from all the way to your power plant.
So when you're flipping the lights on and off, it's the wire just going back and forth?
Hey, no, it's not a wire as it is something that's something goes back and forth. I don't know if I would call it a wire.
Because I know that you're not the one that's
Anyways, so
Are we always just wasting energy when it's just going
Or
into?
you can decide.
Don't worry.
it won't just go into it.
You're trying to decide. So you just decide.
When you it's not going to continue to, if it can't go somewhere, it's not going to keep it going. If that makes sense at all.
It'll stay where it is.
Right, so if I shut the switch off, okay, so if it's off, there's no potential difference because it can't get to the other end. Okay, but when I connect it, it can allow those charged particles to flow through because there is a potential difference now.
So then why is that different when like there's like a break or like a rip in a cord and stuff like that, and then like electrons just like build up and that's when you touch it and you get shocked? What allows? Is it saying that?
A rip in the core.
Yeah. I don't know.
You're talking about like what, a short?
Yeah, sure.
So that's shorts are bad because electrons or current will always take the path of least resistance, and if you like touch a metal wire that is exposed, it's a lot quicker to get to the earth through you than it is
Yeah.
the other alternative way.
So is that saying like you're the thing that reconnects? Like in this scenario, when you touch a shortage, you're the thing that like.
Well, the switch is not a conducting material. So like when the part of the switch that you're touching isn't conductive.
No, I know. I'm just saying like when you flip the switch off, it like makes the electrons stop flowing, and then when you reconnect it, they start flowing again.
Yep.
I'm saying like in a shortage, you're like that same kind of thing. Like when you touch, like it stops moving and stuff like that, and it builds up, and then when you touch it.
I don't. Yeah, it depends on the. I'm not 100% sure on a short. Like because you can still have electrons moving through something that's shorted, but it's probably not going to be as effective. But if you touch that short, it causes it to go through the least path of least resistance. There's very like different kinds of shortages. Okay, so when you flip on a switch, okay, it creates an electric field, which allows us a force to set the electrons in motion, creating current, because current is the flowing of what? Okay? Now, what might be confusing to you, and you may not have thought this, the electrons do not move in a straight line. So like, if this is my wire, and this is an electron, it doesn't just go like this. Does that make sense? Or maybe it doesn't make sense yet, but it doesn't just go straight like that. Okay? What actually happens is, if you look in your book, you should see right on the top right corner there's a little visual. Yes, it moves in a straight line, but there are lots of collisions that happen. Okay, there's a lot of electrons in there because those electrons collide with each other. Okay, are they probably pretty rapid and random motion that we know about what electrons act like? Okay, and so believe it or not, electrons are actually kind of just, sometimes they'll even go backwards a little bit. But overall, they do progress forward. So when you were saying it like pushes all the electrons with it, that's what it's doing. But it's not really fast. So you might be wondering, why does the light switch turn on right away if electrons actually move really slowly net? The net movement is really slow. Okay? The reason why a light turns on right away is because when I shut off the switch, the electrons don't just get sucked back. That makes sense? They're still in the wire. So there's still electrons right next to the light, correct? Okay?
So you're saying that even if they're on the other side, they just still stop moving because they're not going to like.
Yep, they're going to stop moving. Okay? But as soon as I connect it, okay, so let's say here is my light bulb. Right there.
It's a fish.
Okay. You'll see when we do schematic diagrams next chapter why that is the way I wrote that. Okay. And say here is my switch. Okay. When I shut it off, does that mean there's no electrons here?
No.
No, there's electrons there, but they do stop moving. Does that make sense? So I still have a bunch of electrons here, and there's probably more than what I'm showing. Okay? And so even though when you turn the switch on, they don't move very fast, there's electrons right next to the light. Does that make sense? So when you do turn the light on, it causes everything to start moving, and electrons will immediately go through that light. So even though the electrons don't move extremely fast from a net standpoint, the light turns on almost immediately, because when that electric field is created, when you close the switch or allow potential to run through that, the electric field actually travels at the speed of light. So the electrons don't travel at the speed of light, but the field gets from the power source to here at the speed of light. Okay? So if the electric field is made to this point at the speed of light, these are going to start moving pretty much immediately, right? Now they're not going to move very fast, but they're not going to move immediately. That's why when you turn on a switch, you see light pretty much instantaneously. Okay? That's known as drift velocity. Oh, it's up there. Okay. Why didn't I even open up the book?
That's what I was asking.
Sorry, guys.
Worthless.
Worthless teacher. Okay.
Worthless book. No, not
Wait, how
teacher.
did man, worthless book?
Okay. So, drift velocity would be the net velocity from point A to point B. So if I go from here to here over a certain time period, it's not going in a straight line, so the drift velocity is not really high. Okay? Yes?
So is the reason it's not going in straight lines because it's taking after?
No, it's because the electrons move in rapid random motion.
So they just bounce it.
Yeah.
Wait, that's theoretical though, right? Like we haven't actually viewed the electron and seen.
Yeah, I don't know. I'm thinking it's probably theoretical. Yeah.
Because they're probably just.
Why are you tired, Cheyenne?
Waiting
A long night at
Play
the
really
flying
bad there.
practice.
Is drift speeds referring to drift velocity?
It's the magnitude, it's just not the direction. So it's a speed. All right. Okay. Here is, this is known as Ohm's law right here.
Oh my goodness.
Okay. Another way of writing this, sometimes I write it like this.
In our notes, it's like that.
Is it?
Yeah.
Okay. It's the same equation, just solved for a different variable. Usually, I actually probably solve for any one of these three variables, so it doesn't really matter what form you have it in, whatever's comfortable for you. Okay.
Wait, we have no. Oh my
Now,
goodness.
the current of a light bulb, listen up here. The current of a light bulb depends on a potential difference across the power source. So the voltage doesn't help or determine the current, but it's not the only factor that affects it. Okay? So a 9-volt battery is going to give you greater current than a 6-volt battery, assuming you use the same material that you were transmitting that current through. Assuming all the other conditions were the same. Okay? However, it isn't the only factor that determines current. The material that makes up the connecting wires and the light bulb's filament and other factors can affect the current, and that goes into a variable known as resistance. Okay? And we're going to talk about 4 things today that affect resistance. Basically what resistance is, it is kind of what it sounds like. It resists current flow. Okay, or it resists electrons' ability to flow. All right? Sure, you look at it that way. This is one of my. This thing seems silly, but I really like this because I like writing this unit. That's the unit for R. So R is 12 ohms. Isn't that fun? So just write it. Just write once. Just it'll be pleasurable.
Alright.
Oh.
Oh,
That was pretty pleasurable.
oh
That's the most depressing thing of my life.
Yes. Don't feel the drive.
Still less special.
Come outside. We reviewed advanced chemistry outside. All right. I gave a quiz. I didn't have to talk to students. So, for many materials, resistance is constant over a range of potential differences. Now, kind of like the vacuum and frictionless situation, we are going to treat all materials as ohmic materials. What that means is if I change the potential difference across a particular material, it doesn't affect its current. Okay, so if I increase the potential difference, it is going to change the current proportionally. And one way to just show this here is this graph right here. Okay, what this is saying is an ohmic material is if you increase the potential difference, the current will increase proportionally. You guys understand what I mean when I say proportional? Okay, so if I increase the voltage by a factor of 2, the current will increase by a factor of 2. Okay, there are certain materials that if you increase the voltage, it doesn't increase the current proportionally, and it's more of a curved looking graph. Okay, we're not going to get into those types of things. It's a little bit higher level. So we're going to specifically deal with ohmic materials. However, I do want you to know what an ohmic versus non-ohmic material means. An ohmic material means that resistance and voltage or potential difference are proportional. A non-ohmic material means that resistance and the voltage are not proportional. Okay, so you decide whether you want to make a note of that versus
Non-ohmic.
That may be a best question.
Is resistance and current different?
Yes, current is how much electrons flow. Resistance affects the current.
Because you were saying current and potential difference proportionately, but now you're saying the resistance and potential difference.
I said resistance.
Yeah.
So when I say an ohmic material, that's referring to resistance.
What did you just say about resistance?
I didn't think
Did
I
someone
said
write it?
much
Resistance
about.
and.
Resistance affects current.
Resistance and voltage.
No, it's always a.
Yeah.
Oh, I said resistance. I misspoke.
Low temperature increases.
I said resistance.
Ohmic is-
Oh yeah, I should have said resistance. I meant to say current.
Okay, because I already wrote that, and then when you said that, I was like, did I write it?
Sorry guys, I didn't realize I said
So
resistance.
potential difference in voltage, I was.
Not the same, they change the same. Is that what you mean? When you say they're the same, it makes me think that an apple and an orange are the exact same thing.
So if I'm saying current and potential difference increase proportionally, then.
Yes, that means if I increase the voltage by a factor of 2, the current will increase by a factor of 2.
So they are the same.
No,
So
they
then
both.
just change potential difference in voltage.
Yes.
Aren't proportional.
I'm confused with maybe when you say they are the same thing, that means different for you than for me. Because like when I say something's the same thing, I think they're exactly the same.
Yeah,
Like
like it means.
a golf ball and a golf ball are the same.
Yeah. That's what I was thinking, like, potential difference can also be called voltage.
No,
You do?
that's not true.
I've seen.
Potential difference cannot be called voltage. Here's what I mean. Okay, voltage affects the current. Because voltage is your change in your potential energy, right? If you have a higher change in your potential energy, your current or your electrons are going to flow faster. Does that make sense, everybody?
So whatever happens to one of them happens to the other.
Yes,
one.
so if I change one, it will affect the other, but it doesn't mean that they're the same thing. Does that make sense? Any other way of saying that, guys?
That doesn't, that sounds like completely different from
You're really confusing me now.
what. Okay,
I'm trying to understand where your
Current-
mistake is.
current and voltage increase proportionally, and current and potential difference
voltage is potential difference. That's the unit for potential difference.
That's what I was saying, you said they're not the same thing.
I thought you said current and potential difference are the same thing.
No, potential difference.
Oh, yes. That's just the unit of potential difference. I thought you were saying change in V and I were the same thing.
Yes.
Okay. I'm struggling to hear and speak, I guess, today. So what I'm saying is an ohmic material, if this increases by a factor of 2, this will increase by a factor of 2. Does that make sense? If I have a greater potential difference or a greater difference in my potential energy, then my current will be greater by the same amount, because more potential energy is going to cause current to be greater, because it's the force that causes electrons to move. Okay? Now, resistance depends on a few things. So usually a certain material, you can't change the resistance of a material. For example, if I have a wire, a copper wire, okay, it is made up of copper, it's not going to change its resistance material. I can cause some things to make the resistance change, like I could increase the temperature or decrease the temperature, but the material itself isn't going to change, correct? Okay, it's always copper. Copper is always copper. That make sense? Okay? So this, theoretically, unless you change, the only one that you could affect would be temperature. Okay? That'd be the only thing that you could do to change the resistance outside of itself. Okay? So, if this is constant, if this goes up by a factor of 2, this has to what? Go up by a factor of 2. If I decrease the potential energy or the potential difference, then the current is going to be slower. Okay, think of this as the driving force for current. It's what pushes the current. It's the energy associated that causes the current to move, or the electrons to move. Okay? Each material has a certain resistance factor, and they are dependent upon length, cross-sectional area, temperature, and material. Hold on. All right, turn your book then. I don't think it's up there. Turn your book to this page, which is, I don't know.
Colder temperatures.
I haven't explained that yet. I'm about to explain it. Yeah. Turn to this page, 599. Okay? So, here are some things that determine the resistance of a particular material. Okay? First thing is the length. Okay? If every other variable is the same, and I make the wire longer, does it make sense that the longer the wire, the more resistance it would have?
Yeah.
Why? Why do you think the longer the wire, the more resistance?
There's more material.
More material you have to go through, right? More material you have to go through, the more resistance you have. Okay? Yep.
No, you might talk about it.
Okay? Next, it says the smaller the cross-sectional area, the more resistance it has.
So yeah, that would be like thicker. You're saying like as it gets thicker, it's easier to pass through.
Yeah.
Okay.
Yeah. As the area gets bigger, it's easier to pass through. Think of like passing. You should think of how water would act. Right? Water is going to pass through a bigger opening easier than a smaller opening, right?
Have you ever seen that
Okay.
wireless?
Think of the flow of electrons like the flow of water. Now obviously water will flow for other reasons, but it's the same idea. Something is still flowing. Okay? So if electrons have to flow through a longer material, it's going to come into contact with the material more often, causing it to be more resistance. If it's a smaller opening, it's likely to be more resistant. Another thing is the material. Now the why behind that has to only do with the structure of the material. Some materials are structured a little bit differently, so there's going to be more collisions, causing more resistance.
That's the same with temperature.
Yeah, so when you increase the temperature, the reason why a higher temperature is more resistive is because at a higher temperature, the particles in the substance that the electrons are traveling through, for example, if you increase the temperature of the wire, there are atoms in that wire, right? Those atoms are moving faster, vibrating more, and they resist the flow of electrons more because they're vibrating more. Okay, so there are 4 factors. Longer length has to travel a lot further, more resistance. Okay? Smaller area has a smaller area to pass through, so it's more restricted, more resistance. Okay? Some materials are just more resistive than others because of their structure and how they're made up. And the last one is temperature. The higher the temperature, the more the atoms in that material are moving and vibrating, causing electrons to be more resistant in their ability to move and flow through a particular substance. Those are the 4. Any questions on those? Okay. Just a fun group today.
Oh, I am having fun, man. I'm just on the phone.
Couple other things. We done.
I'm not.
Come on.
Potentiometers.
Resistors can be used to control the amount of current within a conductor. Okay? Now, could you change the current by changing the voltage? You absolutely could. Here's why we use resistors, is because a power plant gives you a steady amount of potential difference coming into your house. A lot, like when you have your electrical junction boxes, I don't know if you guys have ever seen those in your house. You push the buttons and it turns it on or off, and we'll talk about that more next chapter. But a power source, like the power plant, gives you a steady voltage. Okay, they don't vary the voltage to your house. Most of it is either 120 volts that go to your house or 240 volts that go to your house. Okay? It's really difficult to have a power plant change the voltage for you, so instead, your materials that you can use materials that have different resistance, which is going to change the current. I don't know if you guys know this, but there's 12 amp wires, or 14 amp wires, 16 amp wires, 18 amp wires, and it has to do with resistance. The bigger the wire, I don't know if you guys ever seen it, a 12 gauge wire is smaller than a 18 gauge wire. Okay? The bigger the wire, the more current flows through it. So like your air conditioners and your furnaces are usually powered by a bigger wire. Okay? It needs more current. It requires more power. Okay? But your light bulbs use a smaller wire because it doesn't need a lot of current to flow through it. They usually use a 12 gauge wire, which is a smaller wire. And I should bring in some wire. I'll have to do that when we do the circuits. This is really not circuits today, but I just want to talk a little bit about that. Okay? So usually your power source coming in your house is constant. If this is constant, the only way to change the current is to change your resistance. Okay? And any of those 4 ways will do it. Salt water and perspiration lowers a body's resistance because electricity can flow through fluids really well. So that's why you don't want to be, blow drying your hair while in a tub. Or you don't want to be sweating while you're doing messing with your outlets or things like that. Like you wouldn't want to be an electrician and just be soaking wet and just be touching wires.
That's why you can't be an electrician.
Yeah, your life goal probably for you is to not ever be an electrician. Okay, you'll be zapped pretty quick.
Why does it do that?
Because water or perspiration allows electrons to flow through a lot better. I don't really know why.
Well, that makes sense because the electrons are all
Like for example, like electrolytes. Like do you guys remember when I used that light bulb in chemistry and I put it in an electrolyte solution and allowed the current to pass through it because it had ions in it?
Yeah.
Ions travel in liquids really quickly, or charges travel through liquids really quickly. I can't remember why that is, but they do. Okay. These are actually cool. Does anybody have in your house, a light switch that can vary the brightness of a light?
Yeah.
That's a potentiometer. Is what it is.
Oh, that's
Okay. Usually it's either like a button that you lift up and down, or it's a thing you spin. Usually, what they do is inside those light switches they have coils of wire, and so when you spin it, it allows electricity to go through either more wire or less wire, which we know if it travels longer, what happens to the resistance?
It's more.
It's more resistive if you have to travel through more wire. And if it's less wire, you have less resistance. So when you spin the knob of the light switch,
It lets out more coils.
well, it moves. I have to. You'd have to see a visual of it, but like it moves, and then the output where it connects to the output changes, and so he will.
Wouldn't it eventually be?
We don't call it a potentiometer, we call it a mood light.
Yes, it changes the brightness.
Well, I know, but if you put it on a lower level, it makes it more resistive. But doesn't that just mean it takes water to get rid?
I haven't used it yet.
No, because remember the electrons are already all the way close to the light bulb.
So you're saying the end.
That's a good idea, I'm gonna take one of this one, got that one, and just play it.
What do you mean by the end? So basically, it's like a coil, a wire, and like something on it that moves and connects to an output wire. So like, if here it's going to travel through this, if I twist it and I move this way here, it only has to travel through a little bit to get to the wire, versus I twist the knob, and right there is where it would lead. This has to travel a lot further, more resistance. The light you see
Garrett's gonna get it.
it has to travel before the wire. It will be brighter. I know.
Garrett, run!
A little bit. I don't think there's a good picture of that.
I was right. That's right.
Remind me, Lauren, I'll pull up a Google image of it tomorrow.
That's all right.
Yeah, I don't know why I just have been waiting for the
Sure, have you done your essays yet?
Hi,